but they've been lovely. So, yeah, today I'm going to talk about a paper, mostly about a paper that is actually a few years old, but Audun, you thought that this might still be interesting to you. So, how many of you have heard about the cannibalization effect? Not everyone. Okay, great, because I have some slides explaining it. So this is work that I've done together with Tom Brown, and actually he did most of the work. So yeah. But first, just a few words about myself. So I do, when I thought about it, I realized I do quite a few different things. Which
you all do quite a few different things.
Which means that I am by no means an expert on electricity markets. But one of the things I do is I've done some papers on global energy systems. I've done recently a paper about future possible global trade with electricity or electricity-derived fuels. And I do some work on biomass. Some of it I'm going to present tomorrow. I often, not always, but often I use this tool, PIPSA or PIPSA Europe, which is a sector integrated energy system model that's open source. And it's now a collaboration between many different groups in the world. Yeah, the talk I'm giving today is about electricity markets. And then I also do some work on hydropower. So as you may know, Sweden and Norway has a lot of hydropower, and therefore it's quite important for us and will be possibly even more important in the future. And I've recently also started doing work about resilience or robustness of future energy systems. And some of that I will talk about at the Informs conference. Okay, but back to today's topic. So what's cannibalization? It's, I don't know, it's kind of a strange word, but anyway, that's what's used, so I'm going to use it. So to explain, this is the typical solar output over the day. I mean, on the x-axis is hours of the day, and on the y-axis is the power output. Nothing strange about that. I mean, solar produces during the day. But what happens when you have a lot of wind, well, actually, in this case, solar in the system? By the way, same principle goes for wind, but we talk about solar because it's a little easier to see. And one figure that's been established is what's called a duck curve. And the duck curve is, it's the net load. So it's the demand minus whatever wind and solar output. In this case, solar. It's in California. There's a lot of solar. And like you can see, the back of the duck has been more and more accentuated as time goes by, which means that, you know, the originally demand was or is higher in the day. But the net demand, so the demand minus the solar, is becoming lower and lower and lower. And what happens then with the electricity price? Well, the red price is the price from 2012. And there you can see it mimics roughly the demand. So it's higher during the day. Well, already in 2016, in 4 years, the price is the lowest during the day. And this is due to solar producing a lot then, and then depressing the electricity prices. What happens then with the revenues? Of course, the revenue is the production times the price, right? So revenues are also coming down, hence the word cannibalization. They eat their own. So that's just the definition. And, I mean, cannibalization is there. Empirically, people have looked at this, and this is an example from a paper by Lina Reichenberg, one of the first papers on this from 2013. And actually the reason that we wrote our paper. But here you can see some empirics on the value factor. So the value factor is, we don't have to go into the definition of the value factor, but anyway, as the market share wind and solar increases, their value decreases. So it's there, and it's been estimated at roughly at 30% penetration level, the value is halved, which means the revenues are halved.
But the value to customer increases.
Okay, so now you're into the
Yeah.
consumer versus
Yeah.
producer welfare, which is another question, yes. But
Yeah, I mean, this is all what we want to do, so it's a good thing. It's not a bad thing.
well, I mean, usually we want to think about welfare as producer plus consumer welfare. And that's the, I mean, that's what we are kind of valuing here. So the total welfare, producer plus consumer, not only consumer. Because you're right, if you only value consumer welfare, then whatever depresses price is great. But what happens afterwards then?
So just without talking too much, I just want to throw this thing because I've been very excited about this for years.
Yeah.
Are you familiar with Elinor Ostrom's work?
Sorry?
Elinor Ostrom, she was the first Nobel Prize woman in economics, Elinor Ostrom.
Okay.
She argues actually, it's very interesting. She has this in her, whatever, Nobel Prize winning 3-page science journal. She has this circle and said the resources, the users, the interactions and stuff like that. What do we want at the end to do with sustainability to make the most out of what we have?
Yes.
If you think from that way, this is not bad, you know. So it's just that, you know, the producers are losing a little bit, right?
Yeah, but
So I just want to put that on the table.
yeah. But that's a very good point, and maybe we can come back to it later, because I think that's highly valid.
Make another comment. So this cannibalization effect, it's not only for wind and solar, it's for
everybody.
for any resource, right?
Yeah, I mean, that's one of the points that I'm gonna try and make in this talk. So, just two definitions of things I'm going to talk about. I'm going to talk about market value. And market value is the average revenue that a technology receives from the market for a unit of electricity. Should be straightforward. So this is the definition of market value in mathematical terms. And what I want to point out is that just like we saw with the solar cannibalization, the timing of production matters. So it's the timing of my production times the electricity price at that time. Right? And the other concept is levelized cost of electricity or levelized cost of energy, LCOE. And that's the average cost to produce a unit of electricity, of energy. And this is the definition. And I just want to point out that, of course, costs are coming into the LCOE, but what also comes in is the availability. So for wind and solar, it's not always windy, it's not always sunny. And that's the case also for thermal generation, right? Sometimes the nuclear power plants are down, but also that they are not always needed. For wind and solar, there's curtailment. So it's not necessary that the actual energy that comes out on the market is the same as the potential maximum, right? It's curtailment. Sometimes it's not needed. If there's too much solar on the market, then they're curtailed. And this is the definition that I'm going to use going forward. So, but because sometimes LCOE is rather used with the maximum possible amount.
So that's the sum of capital and operating cost, is that?
Yeah.
Okay.
Yeah. But what I want to say is that both are dynamic in the sense that they depend on the system they are part of. For the market value, the price is set by the different technologies on the market. So the capacity of solar has an impact on the price. And for LCOE, like I said, it matters whether the energy that a technology produces is needed or if it's curtailed, or for gas, it's load factor, right? So the load factor for gas might be 5% or it might be 60%, which matters hugely for the LCOE. So just a side note, I just want to mention the merit order effect too. And merit order effect is actually just the effect of more zero marginal cost generation coming into the market, that depresses prices for everyone. So everyone gets lower revenues, also the thermal generators. And the cannibalization effect is really the merit order effect, but on steroids. The merit order effect for winners. So what's the problem with all of this?
No,
I mean,
no problem.
okay, your answer.
No problem.
Some people I know, I mean, some investors are now really talking about this as a problem.
Sure, missing money.
Yeah,
We call it missing money in this country.
missing
Missing
money
money
is
that,
mostly
you know,
for gas generators, right?
For everything,
heat.
because you're not getting paid enough in real time to recover your investments.
Right.
Yeah, because it's, yeah.
Anyway, investors in wind and solar in particular are seeing this now, and they take it into account when they make or not make their investments. So, but others have said that it's really a barrier to the energy transition. So this is the thing that will set a bar for the maximum amount of wind and solar, and that instead we should go for nuclear or CCS or something like that. So these are two examples of such papers. The one to the left is again the first paper by, well, kind of first paper about this by Leon Hirt. And it says even in the title that it's the variability that is the problem. And Jesse Jenkins also had some papers about this. He had an op-ed in New York Times, and he says that wind and solar are eating their own lunch. So whether they're cannibals or they're eating their own lunch, I don't know, but a lot about food here. Yeah. Here are some other papers that claim that also in the long term, that's the blue line there. That's again from the Hirt paper. This value depreciation will continue, and it is due to the variability. So basically they're saying that this is inevitable. And here's another example from a paper by Blasquez. He says the paradox being that wind and solar are making less money the more there is of it. I don't know if it's a paradox, but anyway, holds as long as market clear prices with short-term marginal cost and renewable technologies, marginal cost is close to zero and not dispatchable. So he's saying that's the reason why this is happening and nothing else, and it can't be avoided. So market value depreciation has been framed as specific to wind and solar, unavoidable in energy-only markets, and, well, possible to slightly mitigate using flexibility options, but not avoid.
What is value depreciation?
Yeah, it means market value decline, so that the market value decreases with penetration level.
So I said that, I mean, there are opposing views, but I'm sure you will get there.
I think I will.
And I think there is a
No,
question.
I should probably not say
Okay.
Okay.
Yeah, but at the same time, me and many others are doing like future studies where we look at the cost optimal mix, and we find that, you know, there's a lot of wind and solar in the system. So how can these two?
Can I just ask clarification question? I'm not sure I'm convinced, because these low cost, marginal cost, like solar winds, they if we have uniform pricing, they're still making a lot of money, right? Because everybody gets paid, you know, the clearing price.
Well, I mean, the problem from their point of view being that when they produce a lot, the clearing price is very low. Like in California, midday in California, the price is very, very low. And that's when they produce the bulk of their energy, or all of it. Yeah, so how can these two facts coexist? That's what the paper is about. Oh,
It always policy can fix it, and it never fixes it.
okay,
You know, if you look at the history, I mean,
yeah,
let's see what policy can fix it.
yeah. In theory, at least, policy can fix it.
Yeah.
So these are the, we are trying to make 2 points. That this market value decline, it does happen, but it happens under certain conditions. Either under certain policies or out of equilibrium. And that it's really just a consequence of the basic supply and demand effect, that the cannibalization happens because of excess supply of a certain technology. So I'm giving away my points before I start, but here's our research questions that were very much inspired by previous literature that we thought had kind of confused things. So first question is why the setup in market value studies show declining market value on wind and solar. So the why is this happening in those studies? How is this related to different types of policy instruments? Technology specific, and by technology specific, I mean in an American context, it would be the renewable portfolio standards, for instance. So to mandate a certain share of wind and solar in the mix. In Germany, it would be feed-in tariffs, where they paid quite generous subsidies to those who wanted to invest in wind and solar. CO2 policy instruments would be either a CO2 tax, or as in Europe, the EU ETS with a permit price. And as a side note, kind of, what is the effect of flexibility? Which can be transmission, long-term, short-term storage, and yeah. And just to say that the scope here is long-term equilibrium. So we're looking at equilibrium markets, which I will come back to that towards the end, is not the case for many markets today, but that's the scope of our study. because it's been claimed that this also happens in long-term equilibrium. So the paper consists of 3 parts. One is just very simple economics 101 reasoning. And then there's some math. There's analytical solution of this problem, proving what the market value is. And then we implemented it in a model. So there are some numerical results. And yeah, we did it in the same model that Geert used it in the seminal paper from 2013. So we used most of his assumptions, and we used this simple capacity expansion model.
So here he looked at historical data, right? As far as I remember.
Right. So Geert has written about 10 papers about this subject.
Right. Okay.
So, but when he was trying to prove the point that this is the case also in long-term equilibrium, he used this capacity expansion model called EMMA.
So how do you distinguish between long and short-term equilibrium? Like,
Yeah.
what do you mean by long-term?
Long-term equilibrium is when the capacity mix has come to an equilibrium. So, I mean, short-term equilibrium is just that it's basically the merit order, the energy-only market. But long-term equilibrium is when, given the conditions, all capacities have found their optimal amount, or the amount that is just saying the same as that's the solution in the perfect market.
Optimal production amount or optimal capacity?
Optimal capacity.
That's in the line.
As well as production. So, yeah, I think I'm going to talk about this a little bit. So this is just the basic fact that the cost optimal solution, the welfare maximization, is also the result in a perfect market. This is basically Adam Smith and a few other economists. So in that equilibrium, we find a capacity mix that has the optimal amount of different technologies. So there's probably some wind, some solar, maybe some nuclear, maybe some coal and gas, and so on. The point being that they occupy different niches in the energy system. You can't have only wind. You can't have only solar, or you can't have only nuclear, or it's going to be very economically stupid to have just one. So you need a mix, just like you need different things on your plate. And in that solution, the optimal solution, the cost per energy unit is the same as the market value per energy unit. This is called a zero profit rule. And it should be, you know, really basic economics. Yeah. So this was also, you know what? Yeah. So the argument goes like this. Under a VRE policy, so you can think of it as a renewable portfolio standard or feed-in tariff, once capacities have come to a long-term equilibrium. So let's say that we start with this capacity mix here. So there's a little bit of wind and solar, and there are 2 different fossil technologies in my example. So what happens when you apply a renewable portfolio standard is that you are forcing more wind and solar into the system. And I mean, in reality, of course, the the thermal capacities are still there for a long time. But assuming now that we go to the long-term equilibrium, what happens then? Then we have forced in a lot of wind and solar. The fossils have adjusted to the conditions, so now there's less fossil capacity. So within these conditions, the fossil technologies are still the optimal amount. However, the wind and solar is not. Which means that the wind and solar is not subject to the zero profit rule, which means that its market value is lower than the LCOE. So the revenues are lower than the cost. And there's nothing strange about this. It's really very basic.
So that's because they receive additional revenue streams from incentive schemes.
Yeah, I mean, the reason that this can never happen because of these policies is that they don't get revenue from the market, or they get only part of it from the market.
Yes, they get outside.
They have a different outside revenue stream. But previous literature, their variability was kind of mixed up with this very simple fact. But during a CO2 policy, under a CO2 policy, so a CO2 tax, let's say, we start with the same capacity mix. Now, the CO2 price increases the running cost, of course, of anything fossil. And that creates incentives to invest in more wind and solar. Prices go up, and there's an incentive to invest in more capacity that does not emit CO2.
What is being sold? What is the derivative? Clean power, or it's not anymore what used to be just power. Now you're selling clean at the higher price.
Yeah,
so
I mean,
you're selling the different derivative here,
Yeah.
So that needs to be defended also.
Yeah, assuming that
We are having a very hard time with that here today.
I know.
Yeah, so I don't know.
So assuming that the CO2 tax equals the social cost of carbon,
Right.
or even if it doesn't, this still applies. Now, still, I mean, all of these are optimized, so the zero profit rule is valid for all technologies. The market value equals the LCOE. Okay, so this is the simple explanation. And I almost hesitate to present this paper because it's so simple.
Can we ask, going back to Rahman's question about long-term equilibrium, I don't know how you take into consideration the fact that these clean technologies, they are smaller scale, they pay off faster than the ones like nuclear. And so there is this intertemporal effect. So the question is, when is that the long-term equilibrium actually gets reached?
Yeah.
For different technologies, I think it gets reached at different times.
Well, I mean,
And so
the equilibrium.
what is the definition? I think it goes
the
back to-
long-term equilibrium is a property of the whole system. It's not for just one technology.
But things keep changing. You keep building
Absolutely.
stuff. So what is the
Yes.
equilibrium? I think that was the basic definition.
So
The basic question, yeah.
you may argue that markets are not in equilibrium, and I
Yes.
think you are absolutely right. But what we're trying to do here is to kind of tease out the arguments for why wind and solar could not reach a high penetration level. And we do that by, if you want to, we do this theoretical or thought experiment that also others have done.
So isn't it true that, I don't know, I'm just speculating here, over shorter time in the future, these variable resources will recover their investment, and the nuclear energy they'll recover it over a longer period of time.
Yeah.
So sort of sequence of things taking place.
Absolutely, yeah.
So is anybody working on that?
I think so, yeah. And I think that's, I mean, that's an interesting field or, I mean, those are interesting research questions because it's not like I'm denying that there is a cannibalization effect. I'm just trying to tease out what the reason for it is.
I guess what I was trying to say with these different time horizons is that over long time
Mhm.
equilibrium, I think there will be opportunity for these plants to still recover more, although they recovered over shorter time, the basics, and they make up over longer time. So
Yeah.
it depends on where you define the equilibrium. I don't know.
Yeah, I mean, the definition of the equilibrium is where all generators make zero profit.
But that's not
This is-
true for all every technology, is it?
Not currently, but I mean, this is kind of the long-term vision, if you like, where the system should be moving in this direction.
I'm not
In
even clear they
principle.
should be moving in that direction. I mean, because you recover your money faster, right?
Yeah, I mean, I think you're absolutely right that the recovering of the money happens during a transition period.
And
So,
one thing that we are working on the engineering side, I think it's really exciting because you don't have any more really scale of economies. You know, you faster recover things. So it's more of a process of finding break-even solutions where some of the benefits amounts to
Yeah.
investment cost. And it's a sort of different game with these different diverse technologies. That's what I was trying to say.
yeah, I think you're absolutely right. I might come to an example of that
Okay.
soon, hopefully. So we also proved this analytically, and you can look at it and in the paper if you're interested. It's not at all complicated. We formulate a model that just maximizes welfare, very standard. We take the KKT conditions for the optimal solution, and we use them to prove the zero profit rule. And here, I just want to highlight that you see here the LCOE equals the market value, but there's an S also. So different technologies have different market values. Nothing strange about that. It's like your plate with potatoes and meat and vegetables. They don't have the same value. They have different LCOEs and they have different market values.
No storage, right? There is no storage in the model.
Well, we have two versions of the model, one with storage and one without. I'm going to get to that in the numerical result. And this can also be proved for storage, and it's done. If you're interested, you can take a look at the appendix of the paper. So
So you
You
have,
send the paper.
yeah, sure, it's in that. So I was gonna say, you have two problems, don't you? You have the system problem, minimizing the system cost or maximizing system welfare. Then you have the individual generator or technology problem. Is that
Yeah.
how you look at it, or?
yeah, I mean, so we formulated as a maximizing social welfare problem, but then when you take the KKT conditions, you get the prices. And then it's reformulated. So this is basically but it's what Adam Smith claimed in 17 something.
Yeah.
Right, but it's just in,
So you
in math.
solve the system problem and you tease out the prices, and then
Yeah.
you check that the generators recover their costs.
Yeah.
Does the difference in the market value come from the capacity factors essentially of each resource, or is there another?
No, right. I mean,
running
that's,
space?
so it's the different market values in the optimal mix reflect the cost. And they also reflect the value if you want. I mean, solar right now has a low cost, right? The LCOE is pretty low, but you can also argue that it has a low value because it doesn't produce at night. While something that's flexible, such as gas or batteries, they can produce anytime, so they have a greater value. But the point is that in optimality, in long-term equilibrium, these capacities reach these optimums where they exactly balance cost and revenue.
On that note, do you model the chronology, the time? How do you deal with the time dimension here?
There's no time, that's the problem.
Yeah, I mean, it's modeled, yes. I thought I would not delve into the.
That's fine.
calculations,
We
but-
can talk about that later. Yeah.
Anyway, the point is here you can see how the market value changes under a subsidy. So essentially, in order to cover your cost, so in order to cover the LCOE, you need the revenue from the market plus an additional something. And here we call this a feed-in premium. So in this case, we look at it as though you get part of your revenue from the market, but then you need that extra feed-in premium to cover your cost. This is the feed-in premium that's required to reach the optimum mix or the long-term equilibrium. It might be zero, right? Might be sometime. But in our example, it's not. To contrast that, under a CO2 policy, the LCOE is the market value minus what the fossil generators have to pay in tax. So epsilon here, or E, is the emission factor of fossil technology S, and mu is the CO2 tax. So the LCOE is the cost to produce a unit of energy using this thermal technology, using the utilization factor that is there in the optimal mix. And they get the market value they get the revenue from the market, so the market value, but they then have to pay the CO2 tax.
So SS is thermal technologies here?
Yeah, I mean, S is any technology. So, but in the case, I mean, the emission factor of wind and solar is 0.
Yeah.
So,
Right, but on the left-hand side, the feed-in premium only goes to...
right, that only goes to the technology that's subsidized. So from what I've been talking about so far is wind and solar. Okay, so this is the main result of our study. These are the market values for the VRE policy, the red one, and the CO2 policy, the blue one. So we can see, just like all the previous papers, I mean, we show that the market value does decline a lot with penetration level under a VRE policy. So when we use feed-in tariffs or renewable portfolio standard, that is absolutely true. That's cannibalization. The way we did this, by the way, is that we kind of incrementally forced in more wind and solar into the system. So we did what is on the x-axis, the penetration level there. So red, absolutely what's been shown before. But we also show that the reason why we get market value decline is because we have these VRE policies, so the feed-in tariffs or the renewable portfolio standards. If you drive the system instead with a CO2 policy, with a CO2 tax, then you get market value increase with penetration level. Why is the market value increasing? You can also think of it, why is the LCOE increasing?
Have to pay for emission.
Well, I mean, these are the market values of wind and solar, and they don't have to pay for emissions.
The prices increase.
Prices increase, somebody has to pay
Peaker
for
plants.
emission.
Peaker plants are dirtier, so if you need.
Yeah, if somebody has to pay for that, yeah, yeah.
It's a higher carbon cost.
Mhm.
Well, yeah, but I think it's easier to kind of understand this if you say that the market value of wind and solar mirrors their LCOE, so it mirrors their cost to produce. So why is the cost to produce higher with higher penetration level?
Because you have to curtail more.
Yes. So that's what's changing here with the penetration level. The higher the penetration level, after a while, you have to curtail wind and solar. It's also the case that you place wind and solar first at the very best sites, right? So the first 10% or whatever, the best sites. And then you have to incrementally go down. So you have to use lower quality resources. Those are the two reasons why this is happening.
So in CO2 policy case, you do not force in the renewables, right? They become.
Right. In the CO2 case, we drive the system using a CO2 tax.
Increasing the tax. And then
Yeah. We're increasing the tax, but we're just showing them here with the same x-axis because that I should say that there is no nuclear option in these results because that kind of confuses the effector. I will show nuclear results later. But what happens when you apply a CO2 tax, the only thing that this very simple model can do is to invest in more wind and solar. So that also increases the penetration level. Yes.
The CO2 tax, how is that implemented? Is it based on some capacity or during operations of dispatch or as basically a cost of electricity attached to it?
Well, it's just I mean, you use the emission factor for the different, so gas has a lower emission factor than coal and oil and so on. And then we incrementally set the CO2 tax to higher and higher. So we start at 0 and then we set it to, 10, 20, etc. euros per megawatt, euros per ton. Okay, so second result, which is kind of a side note that also others had shown before and also after, is that flexibility of surrounding system matters. So if you have a VRE policy, if you have renewable portfolio standard or something like that, you still avoid some of the cannibalization as well as the electricity price decrease if there's more flexibility in the system. In this case, we added the possibility to invest in hydrogen, so long-term storage, batteries, and also more transmission. There's already transmission in this stylized model, but we added the possibility of investing more of it. So this model is a model of 5, 6 countries in Europe or something like that. And you,
I have a question. So in the beginning, you did mention about the fact that the solar, I mean, I'm guessing there's not much storage in the system. So when the solar output is low, you have to go to fossil power plants and other things.
exactly.
So if I take that model, the amount of fossil energy that you require should stay up, right? You cannot replace it with renewables because if you're assuming that there are periods of the day where you have to use them.
Or you don't serve customers.
But
You can partly, I mean, you can replace them. It's just because there's some heterogeneity in terms of wind power output.
Yeah.
And wind and solar also have some complementarity effect.
So
But it's very costly.
yeah, my question is,
It's costly.
Yeah.
I mean, that's
okay. What is costly?
I mean, to scale up more and more.
Yes, yeah,
renewables, right?
Got it.
Yeah.
So, but at some point that also has to, that probably will plateau somewhere, right? That where does the impact of peaker plants and all that, does it show up somewhere that?
I think I might,
Okay.
tell me if you don't get the answer soon.
Okay.
So here, I just want to highlight that you can see, especially on the electricity price, so the black lines, that it really plummets at something like 50% penetration level. And that's exactly what you asked, that once you hit a certain penetration level, then whatever more wind and solar you invested, it doesn't matter, it doesn't help because it's anyway curtailed, most of that energy. So at that point, if not before, you definitely need the flexibility measures. And you can also see that also mimicking previous results, that the market value decline is still there. So the red line, the dotted red line, but it's slightly milder. And here's the same result, but for the CO2 tax. So the light blue line is the inflexible system, and the dark blue line is the system where there's more flexibility. And yeah, think about this as LCOE, so the cost to produce a unit of energy. And then you can see that that goes up very sharply at something like 60–70% if there is no flexibility in the system.
There's a question previous slide I'm reading from the online participants.
Mhm.
It seems that under the CO2 policy until around 10 to 15% wind and solar penetration, the market value still decreases. After that, it starts increasing.
Right, so so that first 10% there, actually, I remember us talking about this, but I can't remember why that happened. In my mind, it shouldn't happen. Answer is, I can't remember.
Because
Sorry.
you're not at equilibrium, it's transient, so you can't claim any optimality there. You haven't reached, this long-term equilibrium is confusing, because if you just have 10%, you are not at the long-term equilibrium.
Well, you are, because you are at the long-term equilibrium given that CO2 price. All of the points on the blue line are long-term equilibria given a certain CO2 tax. So the valuation of CO2, of emitting CO2 changes. All of the points are long-term equilibrium. Yeah.
Why wouldn't that be why wouldn't it increase due to the fact that at your kind of best, like, middle of the day, whenever is best for wind, wouldn't that decrease come from the fact that you haven't saturated those points in the day at low penetration levels?
Yeah, but you have saturated them even less at 1% than at 10%. In my mind, it should be steadily increasing the blue line, and yeah. But I'm sorry, I can't explain it, but yeah, it's an anomaly in the numerical results. Okay, yeah. So what we can see here again, also with the CO2 tax, that the LCOE for wind and solar is much more stable if you have flexibility in the system. And that's not strange because you curtail less. It's as simple as that. So how much time do I have?
10 minutes.
Okay. I'm gonna skip this. We also did this for nuclear, by the way, just to show that the same thing goes. It's really about too much capacity lowers the value, but it happens much later for nuclear. So
Is that, sorry, that detail, but is that the dispatchable nuclear then? Yes.
yeah, so it's a very simple model. It's very dispatchable. This is only due to the utilization factor. So I just want to say that the earlier papers that claim that this all had to do with variability, they're kind of correct, in the sense that, yes, variability of the technology matters, but you can completely avoid the market value decline if you drive the system with a CO2 tax. But if you do have a renewable portfolio standard or the like, you will see that more variable technologies have a faster decline. So in this case, I mean, what's more variable is maybe up for definition, but I would argue that solar is more variable than wind because it changes between 0 and 100% like all the time and has a lot of zero values at night. So you can see here that solar, that's the yellow line, has a faster decline than wind, which is the blue line. And wind and solar combined, it performs a little better than only wind. So yes, they were partly right. Now, coming back to one of your questions, I think, what we've seen happen in reality is with the feed-in tariff in Germany, they got a lot of new wind and solar, but the thermal capacities are still there, which is the case in non-equilibrium because things take time basically.
Right.
They still have a lifetime of 30 years or 50 years or whatever. Yeah. So I would argue that Germany is probably not in equilibrium.
Nobody's ever in equilibrium. I think this is just economic fiction,
Yeah, it's exactly, it's economic fiction, but
I'm sorry. I mean,
I'm mostly in the economic fiction world.
no, I mean, how can you use it when you're never there? It's just like,
The shining
then I
light.
think Daniel is doing his thesis, add uncertainties.
Yeah,
What is the value of all of these under uncertainties now?
yeah, that's a
It
good
just
question.
completely goes away. I really resonate with Rachman's question. I can't define the equilibrium for
Yeah.
markets anymore.
I
I'm not an
actually have
economist,
another
so.
paper about that.
If you have some reading, it would be good.
Yeah. So again, coming back to the real world, what happened with the electricity prices during roughly the same time here is that first, and now we're in Germany again, it decreased between here 2008, 2016, with increasing shares of wind and solar, electricity prices decreased. But what happened then after 2016?
CO2 taxes or?
Yeah, that's when the EU ETS price started to rise. So here we can see the market price. So it's the average electricity price in Germany. And the EU ETS price, that's the red one. So you can clearly see that it started to rise in 2016 and then electricity prices also rose. And the market values of wind and solar also rose. Yes.
Does Germany have an additional tax on carbon?
No, I mean in Europe, those industries that are part of the EU ETS, they are exempt from other carbon taxes, as far as I know. I mean, that's the case in Sweden. I'm pretty sure that's the case in Germany too.
Well, what happens when the EU ETS price is significantly less? Because I know in some countries it's over €100 right now for the carbon taxes, and the EU ETS price, I don't believe is that high.
I looked the other day, it's 77 euros. But yeah, you're right. I mean, for instance, in Sweden, there's a carbon tax of around 100 euros, but that's applicable mainly to gasoline and diesel.
Okay.
So it's not everything. And yeah, the industries that are part of the EU ETS, they are exempt from the carbon price, or sorry, the carbon tax,
So like
which are
gas-
national things, right?
Yeah, so gas doesn't have to pay the Swedish price, they would have to pay the EU ETS.
EU
price.
ETS, yeah, exactly. Okay, so some conclusions. Now coming back to the research question, why does the setup in market value studies show declining market value of the wind and solar. And it's really because the externality, the CO2, is valued outside the market. And then the market, the total capacity mix is out of equilibrium. There is too much wind and solar given the CO2 price. So again, coming back to these different policy instruments, the market value declines with penetration level for technology-specific policy instruments such as feed-in tariffs, renewable portfolio standards. But with the CO2 policy, it doesn't. It rises, in fact, at least in our ideal setting. And there's an effect of flexibility, so storage, transmission, etc. It can mitigate but not avoid the market value decline. So what I would like you to take with you from this presentation is that the market value decline is a result of policy choices. So instead of valuing the CO2 within the market, VRE is subsidized from outside the market. And I think, at least in the US, this has also been an option that's politically viable while talking about the CO2 tax is not, as far as I understand it. So to conclude, I think the market value concept should really be used with caution.
Yep. But for one more reason, I think I'm not an economist, but the way I'm thinking about this is really one-sided market. You know, there is no demand bid here at all for energy or for clean energy. If you were to redo this with demand bids,
Demand bids for clean energy.
For everything, the results completely change. Adam Smith is, I have supply and demand and they intersect. Here we don't even have a demand.
What do you mean? We don't have a demand for
I think the whole objective is to increase the market value of supply. Because solar is supplied, thermal is supplied, but the demand is customers being served. And they should have some real markets, you know. They should be buying energy.
They should have an incentive to buy when solar is producing. Is that what you're saying?
There is no information there at all about what the demand is doing.
No, I mean, what we did in this study, I think.
I'm not criticizing this study. I'm just saying that most of the studies, they look at, okay, it's bad for clean energy, it's going to lose value, market value, but at the end of the day, all that is serving something. So we should have two-sided market.
But is there that much demand flexibility?
We've had
There should be, but
we've had very difficult discussions at FERC level because of this.
Yeah.
Because in the US, it's state responsibility, it's not federal.
Yeah.
And the policies comes from federal. So we actually don't resolve this issue.
No.
This is just building open loop. I don't know how much I need. I'm thinking as an engineer, right? I'm designing this, but I don't know what am I supplying. And so it can grow, and I don't even when the equilibrium is met.
Yeah.
This is sort of more of engineering concern about where is the equilibrium. You have to supply and demand. That's what Adam Smith is saying, but not just supply. And I don't know how you deal with this issue. I understand externalities. I understand the point of the talk. I'm just asking a little broader question. Is anybody worrying about customers?
I don't know what you mean by worrying about, but maybe this is a discussion for the lunch because I just feel
Thank you.
Yeah, I'm pretty much done.
Thank you very much.
Yeah, and as a side note, I tried to do something more about